In this video, I'm going to discuss ways that we can sort of predict whether we're going to get substitutions or eliminations and which substitutions, eliminations that we will get. And so I've said in previous videos that these substitutions, so the SN1 and SN2 and the eliminations E1 and E2 are all sort of in competition with each other. And of course, the E1 and SN1 are sort of mostly in competition with each other, and then the E2 and SN2 are more in competition with each other. But then there are ways of, trying to predict whether we get the unimolecular or the bimolecular mechanism. And so the reason that we have this competition is that most bases are nucleophilic and most nucleophiles are basic. And so in previous videos, I even kind of said that in some ways they're kind of the same thing, that bases and nucleophiles are the same thing. As we've seen in the previous few videos, that this isn't sort of completely accurate, that things like steric hindrance can reduce the nucleophilicity of something while maintaining or even increasing the basicity of something and things like that. And so nucleophilicity is a lot more of a kinetic thing, where basicity is a lot more of a thermodynamic thing. But it is the case that a lot of bases are nucleophilic and that a lot of nucleophiles are basic. And so, we can't really say that there's, one, it's either one or the other, that, strong base is strong nucleophile or strong base is weak nucleophile. There isn't any hard and fast rules about that. We also know that many solvents can solvate ions or react as nucleophiles or both. And so, if we have like a protic solvent, so if we have something that looks like this, this can obviously solvate ions, so the oxygen could solvate a cation, and the hydrogen here could solvate an anion. But this also has these lone pairs on it, and so it can actually act as a nucleophile as well. And so it could bond onto another atom, onto our substrate. And so these can act as solvents and as nucleophiles themselves. And so real reactions, as we will see, are not always as neat as the chemical equations that we use. And so we cannot always predict that there's going to be one unique product or one unique mechanism. And in fact, we're going to get a mixture of these things. So just kind of as a review, so remember our SN1 reactions, where the rate is dependent on just the concentration of the substrate here. We have the slow step, which is where the leaving group is leaving here, leaving us with this carbocation, which then can be attacked from either side by nucleophiles. So this isn't being bound to by two nucleophiles. I'm just showing that this can be done on either side, and so we can get the racemization here of our product. So the nucleophile can attack that carbocation from either side, and so that's the fast reaction going to the product there. Then our SN2 reactions, which is dependent on the concentration of the substrate and the nucleophile. The nucleophile comes and attacks the carbon, which then sort of pushes off the leaving group. And we get this inversion here, where we first had the R groups kind of pointing more towards that way, and now we have them pointing more towards that way. And so if our carbon is an S, it will become an R. If it's an R, it will become an S. So we get that inversion there. Then our E1 reactions, which are similar to the SN1 in the first step here, where we have this slow step where the leaving group leaves, forming a carbocation. But then we have a base here. So this kind of gets to where that thing about the bases can be nucleophiles, nucleophiles can be bases. In our SN1 reaction, we just had a nucleophile coming in onto that carbon, but now we have a base taking this hydrogen. Well, if this base is also a good nucleophile, well, I guess with SN1 or an E1, it doesn't even have to be that good of a nucleophile. It can come in and bind to this carbocation here, but we can also have it take this hydrogen and do this elimination reaction to form the double bonds. Then with our A2 reactions, we now are dependent on the concentration of the substrate and the base. We are taking this hydrogen, which is usually anti-coplanar with the leaving group, and so this will push the electrons down onto this bond here, and then the electrons on this bond will go onto the leaving group here, and we are left with the double bond right here. All right, so some rules of thumb for predicting reactions. So I call it rules of thumb because these aren't like hard and fast rules. These are just ways of thinking about it and trying to predict what our major product is going to be. So again, these things are in competition with each other, so you're going to get a mixture of the products. And so we're just trying to figure out like what the major product is going to be. And so if we have a strong base, this is going to favor the SN2 and E2 by forcing the second order kinetics. And so if we have this methoxide here on these ones, whether we have it on a secondary carbon here or on a tertiary carbon here. So if it's on a secondary carbon, we can get the SN2 and the E2. And so that nucleophile on the secondary carbon can sort of access this right here to push off this bromine right there. Whereas on the tertiary, it's going to have more of the steric hindrance that will block the nucleophile from getting in. And so we're going to get E2 on here. So the SN2 is not going to perform well on the tertiary carbon because of that steric hindrance. Whereas if we don't have the strong base, so we just have the weak base, so we don't have the methoxide here, we just have the methanol right here, what we're going to see then is the SN1 and E1 because we don't have that strong base that's going to either attack this carbon or remove hydrogens off from neighboring carbons. And so that's going to favor the SN1 or E1 if we have only weak bases here. All right, so another rule of thumb, primary halides usually undergo SN2 reaction and occasionally the E2 reaction. So we have this bromine here on this primary carbon right here. And so with the primary halides, they usually undergo SN2 reactions. And that's because a primary carbocation is very unstable, and so it's probably not, this bromine isn't just going to leave on its own, so that slow step of the SN1 or E1 reactions is not going to occur. So if we add these silver salts or high temperature, we can try to force an SN1 or E1 with rearrangement. And so up here we have this strong base, which is also a strong nucleophile here. Here we just have this weak nucleophile here, and or this weak base anyway, and we're adding this silver nitrate in heat, and so we can try to force the SN1 or E1 with that. But usually with the primary halides, they usually undergo the SN2 reaction and occasionally the E2 reaction. All right, the next rule of thumb is that tertiary halides usually undergo the E2 reaction if we have a strong base, or a mixture of the SN1 and E1 if we have a weak base. And so we have this tertiary halide here, so this bromine right here on this tertiary carbon, and we have our strong base right here. And so the tertiary halide is going to have too much steric hindrance to undergo the SN2. So this carbon right here has too much steric hindrance with these methyl groups on it to have the nucleophile come and attack that. And so this is actually going to favor the E2, whereas remember up here when we're on a primary carbon here, then it's going to favor the SN2. And so when you start adding more steric hindrance on there, you're going to move it towards favoring the E2 reaction. And if we don't have this strong base here, so without the strong base, without that methoxy there, then this is going to favor the SN1 and E1, because on this tertiary carbon, the bromine is going to be more likely to be able to leave because we have that more stabilized carbocation. And without the strong base, we're not going to be able to deprotonate that or to attack that tertiary carbon. So that will favor the SN1 and E1. All right, our next rule of thumb here is that the reactions of secondary halides are the most difficult to predict. And so we talked about, the primary halide is going to favor the SN2 and somewhat the E2, and when we have the tertiary here, then we're going to favor the E2 rather than the SN2. But when we get to the secondary halides, then it's more difficult to predict. So a strong base can favor the SN2 and the E2, or a weak base and good ionizing solvent can favor the SN1 or E1. So those are going to be the ways that we want to try and predict whether we're going to have the bimolecular or the unimolecular mechanisms here. So the bimolecular is if we have a strong base here, and the unimolecular is if we have a weak base and a good ionizing solvent. But in both cases, so up here, we're going to get a pretty good mixture of both SN2 and E2, and down here we're going to get a mixture of both the SN1 and E1. So that's a bit harder to control whether you get the substitution or elimination when we're working on secondary carbons here. All right, so some nucleophiles and bases favor substitution or elimination, and so this has to do with the nucleophile or base rather than the substrate. So above we were talking about how the secondary carbons on these substrates are going to be a mixture, but the way we can sort of control for whether it is a substitution or an elimination is with the nucleophile. So if we want mostly SN2, we want a strong nucleophile but a weak base, and so the iodide can work for that. So the iodide can work well as a nucleophile for the reasons I've discussed in previous videos, but it's a pretty weak base. Whereas if we have like this tertiary methoxy here, or I guess ethoxy here, this is a strong base because we have this negative charge on it, but it's a weak nucleophile because we have all these substitutions on it, which is going to give it more steric hindrance. So this is going to work well as a base, but it's going to be a weak nucleophile, and so that's actually going to favor the E2, the elimination reaction for that. So yeah, those, like I said, are sort of the rules of thumb here, just to sum up. Strong bases favor our bimolecular reactions here by forcing these second order kinetics, whereas if we have only weak bases, then it's going to favor these SN1 and E1 here, because a weak base or weak nucleophile isn't going to, deprotonate or attack that carbon very well because they're weak. And so it's going to give more time for the leaving group to just leave on its own. So the primary halides usually undergo SN2 reaction with possibly the E2 here, and that's because the primary carbocation is too unstable for these unimolecular mechanisms here. But if we get rid of that strong base and add the silver nitrate and the heat here, we can try to force the unimolecular mechanisms here with rearrangement. So tertiary halides usually undergo E2 reaction if we have a strong base, and that's because we are now sterically hindered on here, preventing the SN2 on there. And so if we then have a weak base instead, we can try to get the SN1 and E1 reactions here. So the reactions of secondary halides are the most difficult to predict, as I said. If we have a strong base, that can favor the bimolecular reactions here, whereas if we have a weak base and good ionizing solvent, we can favor the SN1 and E1, so the unimolecular reactions here. But we will get mixtures of products on the 2' carbons. But then if we have a strong nucleophile but weak base, we can push it more towards the SN2 on the secondary carbons, and if we have a strong base but weak nucleophile, we can favor the elimination by molecular reaction here. But anyway, that was what I wanted to talk about in this video. I hope you found this useful, and I will see you in the next one.